Good afternoon, all, and thank you for joining our Steel Group colloquiums. It is my pleasure to introduce our today's speaker, Peter Jones from Tata Steel R&D UK. Peter is the Automotive Programme Manager at Tata Steel R&D. He did a technical apprenticeship in the steel tube industry before moving into the automotive sector as a body-in-white designer at Jaguar and Land Rover, which were separate companies before joining Rolls-Royce and Bentley motor cars as the BAW design manager. In 1999, he joined British Steel in their automotive sector unit and have had various roles through the merger with Hoogovens into Corus and now Tata Steel. He has been a team member of the WorldAutoSteel's e-motive project for the last 4 years, developing a fully autonomous electric ride-sharing vehicle concept to showcase steel, and have now started the tech transfer, where they present the results to OEMs, major tier 1s, and university. Peter, thank you very much for accepting our kind invitation to present this talk, and floor is yours.
So I'm going to give the presentation that WorldAutoSteel has developed, and it's the same presentation that's gone to all of the OEMs around the world, actually, not just Europe, but all over the world. And we're now starting to roll it out to universities as well. So it's the first time I've given it to the university. I've done JLR, and Nissan and Ford in the UK. So, table of contents, a quick introduction to WorldAutoSteel, and why we've done the project, talking about our advanced high-strength steel grades that we've used. Look at the vehicle, the body structure, and the battery concept. I've got one slide on vehicle sustainability and a Q&A session. There's some links at the end of the presentation to the project report and various downloadable files that you can have a look at. But I will share this presentation with you anyway, and Prakash said he'll email it around to you all. So, quick question on who are WorldAutoSteel. They are the automotive group of World Steel Association, and the steel companies that you can see on the right hand side are the companies that funded this project. We all put the same amount of money in, and as you can see, there's 3 Europeans companies in there, Arcelor, Verst, and ourselves. And when we go to the vehicle manufacturers, all 3 companies go together, and we take it in turns to present. But for universities, just handed by the host company. So it's why I'm doing it today. And you think about the motivation for doing this study. The automotive sector is undergoing the most rapid change in 40, 50 years. And this transformation shifts our thinking from the movement of vehicles to the efficient movement of people and goods. And there is a global shift to achieve net zero emissions by 2050. It is a goal that is 25 years away, so quite distant. But the steel industry is working hard to broadly understand all the factors that must be addressed in order to get us there. In the last 5 years, WorldAutoSteel has conducted extensive research into global trends such as urbanisation and disinterest in vehicle ownership amongst the young and the old, and especially prevalent in major megacities characterised by pollution, congestion, limited parking, and changing attitudes towards vehicle ownership. And that was the motivation for doing the project. So what we've done is develop body structure from a clone sheet of paper that is fully autonomous ride-sharing vehicle. This is the 6th WorldAutoSteel project that has been happening over the last 25, 26 years. We started off in 1998 at Allsab, and we're now in the project started in 2020 for Steely Motive. And the key features are level 5 autonomy, and level 5 autonomy means no steering wheel, no pedals, no driver vehicle interaction. It's designed to meet or exceed the stringent high-speed crashworthiness standards that we have today, or we have in the near future that we know about. It's engineered to be affordable to manufacture, to own, or to use, and it's planned for sustainability. We put this slide in only recently because we get lots of questions. So it's SAA level 5 autonomous. It's designed and demonstrated to be a virtual concept level, so there's no physical prototypes going to be made. It has consideration for hardware and mechanical vehicle parts, so we'd need to make this vehicle go on the road is packaged within the vehicle shape. So it has got space for the radar, the LiDAR, all the cameras, etc. that it needs. It's compliant to the latest and future global vehicle requirements. And it's one of the world's first fully autonomous vehicles with available design and specification data. As I say, there's no physical prototypes going to be made. And it's not for manufacture today, it's for manufacture somewhere about 2035. Talking about the material grades, we asked all of the steel makers within the group to share with us confidentially their new grades they have in development, or grades that they think they will have in production from 2030 onwards. So all those grades were given to WorldAutoSteel, and they then anonymised them, so one steel company couldn't tell what another steel company was doing. But there's a lot of the 3rd gen advanced high strength steels in there, medium mag plus others, and all the 3rd gen dual phase and complex phase grades in there. If you look at the evolving steel grades that are being developed, to go back to 1998 when we did Tulsa, the original ultralight car, there was 11 high strength and advanced high strength grades. When we did future steel vehicle in 2011, there was 26. But today, that has now changed into 64 grades that could be available to vehicle manufacturers around the world. For a grade to be included in this list, it had to be available in at least 2 geographies around the world, so one in Asia, one in Europe, for example. So the parts can be readily made with any grade that the OEMs pick. There are 64 grades there. We contracted Ricardo to do our engineering. They didn't use the 64 grades, but they concentrated on the right grade in the right place. So some of those are not used, but some of them are standard grades that are available today, like DP600. This is a view of the vehicle. Yes, it's fully autonomous, so the people are facing one another. They're not facing forward. It's 2 variants. This is the small one, the SEM1, which is the 4-passenger urban city mobility. Front electric motor, level 5 autonomy. It's got a curb weight of just over 1,500 kilograms and a top speed of about 120 kilometers an hour. Just superimposed. I think that's the outline of a current Golf, just on top of it to give you a view of understanding of how big this vehicle is. It's quite tall because we are sitting on top of the battery pack, but a lot of electric cars, if you notice, are getting taller as well. But it is shorter than a current C segment car. And this is the SEM2, which is the longer wheelbase version, which has got six passengers, and that's for intercity mobility, maybe going to the airport with your luggage. It has got 2 motors, front and rear. It's 400 millimeters longer than the small version. Again, level 5 autonomy, and that's 1873 kilograms. Again, the same top speed. Thinking about the vehicle layout inside, we've chosen the 4 passengers to sit facing one another. We went through various scenarios trying to get more people in, but we felt that the 4-seater facing forward was the right one to use. It's preferred for communal ride sharing instead of having everybody facing forward. It gives you a spacious open interior. It does drive down a requirement for a flat floor with obviously no tunnel, etc. in the middle. It does put the front occupant very forward in the car, which drives the higher roof as well. So you haven't got a bonnet as we have today on most internal combustion engines or our current electric vehicles. And it's also disabled user-friendly. The doors will open wide enough to get a wheelchair in, etc. Part of the very early project that we did in 2020 was actually design upon the style. We went through various iterations of on our monthly meetings, answering various questions to give the stylists some feedback on what direction the exterior would look like. Obviously driven by the seating position as well. On the left-hand side are some of the styling views that we're given. We picked the 4th one down actually, although we've lost the bike rack at the front. But that is the vehicle. It's called a steel lattice structure. That is still as it is today. You look at the 4th picture down on the left-hand side. The doors were slanted. We didn't like that. It didn't help you get a wheelchair user in, so we made them more upright. It is a taxi, and it's really good if you can get the doors to open very wide for ingress and egress. Looking at the materials that we used, we have the purpose-designed body in white for fully autonomous. It hasn't got a B pillar as we understand the B pillar today. The B pillar is part of the doors. It's stamped, fabricated, high volume solution. There's 204 parts in there. One of the obvious changes that there's no body side outer panel as we currently have them. The doors actually cover the structure, so we felt we could do away with the body side outer panel. The little pie diagram in the middle shows the various steel families that we've used. There is quite a bit of press-hardened steel in there, both the 1500 and the PH 2000, which is now becoming available. But the body in white weight's 282 kilograms, which is lighter than a lot of vehicles of this size. And the average tensile strength of the material is 1259 megapascals, and that's obviously driven by the boron 2000. Look at where we use the press-hardened steels. The door ring and part of the front crash structure uses the hot stamped parts. We have Martin Citics, the water ice strength, cold stamped, roll form parts, where the geometry will allow us. We have dual phase and complex phase steels, where they're most appropriate. The front crash rails are DP 800, if I remember rightly, to give us the crush. We have a floor that's made of DP 800 as well. There are some third generation steels. There's a couple of hydroforms on them, on the rear, to go around the trunk or the boot area, and for the rear crush. And there's some high strength low alloy steels, as we currently use them. You look at the markets where the steel companies are, you will find that most of the third gen steels are from the Asian countries, and Europe is going down the press-hardened steel route. So you have to have this balance, and because it was a WorldAutoSteel program, we had to have all of the areas steel grades used. If you look at where we have used the grades and used the gauges, as you appreciate in a vehicle structure, you have a need for high strength, but you also have a need for stiffness. So the panel gauge is determined by its stiffness and by its crash and durability. We can optimize the vehicle structure down to 0.5, and we go up to 2.4 for the shock tower mounts. The average gauge thickness is 1.23. So we've used thickness where it's needed, and we've taken it away where it's not needed. There is a challenge to make 0.5mm parts. You have to be very careful, because in its raw stamped state, until it's fixed into the auto structure, it's not very stable until it's welded into its assembly. And these are some of the fabrication methods that we used. Roll forming, where we can make long components with a uniform shape. Periodic blanks and hot form blanks, they're both in use today. Cold stamping, we know and love. There's a little bit of hydroforming on the rear end and on the B pillar within the door section. And there's something called roll stamping, where you can, it's like a roll forming, but the rolls have got shape on them, so you can make some shape you can roll some shape into the roll form. And that is predominantly available in Asia. And that's the pie diagram of where the parts are. So nearly 2/3 were cold stamped parts. A third was hot stamped. A few little bits of roll form and roll stamping. So these are the 7 key innovations that we came up with. So we've got a pillarless open box open structure. We've got extended passenger protection zone. I'll talk more about it. We've got a very short front crash structure. Again, I'll talk about that. A novel offset crash glance beam. Show that in action in a little while. But if you're doing a fixed barrier, or you're doing a short overlap crash test, the front rails have to perform differently. So it is a challenge to get them to bend and to crush when you want them to in the right test. So virtual B pillar in the doors. We have a rocker section for side intrusion. We've got the DP 800 hexagonal boxes made by roll forming. which were all within the sill section, which they crushed slightly during the side impact. And we've got an industrial first battery carrier frame. Talk about that in a few minutes. Now, talking about the vehicle crash, on the top picture there, the little green dot is where the driver or the passenger's head is when you're sitting in the front, and you're obviously well away from a crash zone. On our vehicle, because you're sitting backwards in the front of the vehicle, and we've got a very short front end, your head is a lot closer to the impact area. So what we have is, in effect, is a reduced, compromised front crash zone, less space to absorb energy, less space to deflect the vehicle, which is why we've had to use some PH2000 in the front rails to give us the right levels of intrusion, lack of intrusion, the front end during the crash, but obviously not pass all the energy onto the occupants. So this is some views of the front crash performance. The top one is the US fixed barrier, 56 kph. The bottom left is the SORB, so the short overlap rigid barrier, which is at 64 kph. We spent a lot of time making sure that our vehicle glanced the barrier and then moved off. If you hit the barrier and the vehicle sticks on the barrier, you do put a lot of load onto the passengers. The VWID3 vehicle you creates 59G passenger load, whereas if you can glance off, it's about a fifth of that. On our test here, our G rating on the passengers is about 13, if I remember rightly. And then you can see on the right-hand side the movable barrier that we have in Europe. Vehicle performs well in those, and the ODB, and they're both fine. We did achieve a good rating for the IIHS SORB test, and good is the highest rating that you can have. So front crash was really good. Talk about the emotive battery concept. On the left hand side is a Gen 2 type battery where you have a housing and bottom plate, and battery modules are then bolted into there. Then that has a top cover, and then that's all mounted underneath the vehicle. We've taken a slightly different approach to save weight, where we have the housing, the battery housing is part of our body-in-white structure. And then we have some cross members and longitudinals, which form the innards of the battery box. And that is assembled with our battery cells, and then that is offered up underneath the vehicle, and then a cover plate goes on it. There's an animation running to show that. This is the battery box is being built. It's upside down. Body-in-white structures and the battery modules being assembled. We have a committee where we go and ask various questions. We asked people like Mercedes, NIO, I think it was Toyota in Japan, whether this is a no-no or whether they could be adopted in this way. They all said manufacturing won't like it, but it's a really good idea because it saves a lot of weight. So the benefits of doing that, on our design, we save 37% of the weight of the battery box. We got improved NVH. no compromise to safety. Improved our package and enabled us to lower the floor height and give us a flat floor. It did improve the access to the flat battery modules because you can then just drop them out afterwards. You need to repair them or change them for any reason. The downside is manufacturing, you're not going to like it. But this is just some more views of the battery box as it goes together. But we have body-in-white structure that we bolt in when it's fitted, and the various parts of the battery modules underneath, all assembled upside down. Then that is fitted into the battery reception area underneath the vehicle, and then it has a cover plate on. You can see there's some high-strength steels in there, and there's some trip material to allow us to get the shapes and the flare on the ends that we like. Roll formed and roll stamped Martin Citic 2000 to give you side impact performance. Just a section across the floor showing the battery modules where they're mounted. And we have a composite floor. It's made up of 4 pieces of steel, but it makes a box section which you need to withstand the various bollard tests that there are around in the world, where these vehicles can get lifted up in the air by car park bollards. Some tests around, so we have to design the vehicle so that it can be lifted. It will be lifted up, but won't damage the battery modules. And this is the floor. So we've got a HSLA bottom plate. Then there's some HSLA, and they're like a honeycomb section. They're pressed to give them a bit of depth, and then DP800 bottom plate, the Martin Citic cross member in there to give the protection we need for the vehicle being lifted up at these various impact locations. This is this side impacts. This is the pole test. Current legislation, the pole is aimed at the driver or the H point. Because we are sitting the passenger the wrong way around, this one is aiming at his head. We've also did a test on the centre of the vehicle and towards the end of the vehicle. We beat the legislation quite easily. On the barrier test, because the vehicle's quite high, we tend to pick up the sill where those hexagonal boxes are, and we pick up the B pillars as well. So intrusions into the car are well within the allowable limits. Another look at the battery, the rocker absorbers that are in the sill, the battery boxes, and the way that the body-in-white reinforcements are mounted off the floor to give you some protection both at the top of the battery box, sorry, battery module, and at the bottom of the battery module. The B pillar is press-hardened steel. On the bottom, it's the standard 1000, 1500 one. The uprights are the higher grade. It's a 4-piece tailor-warded blank. So those components, being out of high-strength steel and their geometry shape, give you the stiffness and crash performance that we require. A little talk about the path to net zero. Where we are at the moment is that everybody is placing weight down on their vehicle. Used to be for tailpipe emissions, it's now for range. we are all striving to use reduced CO2 steel. We did currently, blast furnaces, before we switched them off, we used about 25% recycled steel in there. Now we're going to our electric arc furnace, which will be ready in a few years' time, where we'll be up to 75–80% recycled steel. But the OEMs have also got to talk about decarbonising battery production. Batteries are heavy, but also at the moment the average occupancy of any vehicle is about 1.4. As you go further into the future, we need to have more people in cars, so we need to aim to achieve 100% net zero by using 100% reduced CO2 steel, decarbonise the battery production, but also need to do something about the electricity grid mix as we go on in time. These statements are easy to say, but really, really difficult to do, and it's going to take a lot of effort from both the governments and around the world, but also the steel and the material manufacturers. So, as a summary, the Automotive Programme has engineered an innovative vehicle body and battery structure, taking into consideration the freedoms and challenges offered by full autonomy. So we've got to use the application of a complete steel grade portfolio that the vehicle demonstrates safety. Its competitive weight, it's competitive in its design for global high volume production. It's demonstrating a path towards net zero emissions. If you want to read the full engineering report, you can download it from that website. Excuse me. Or when you've got the PDF, you can scan that QR code. There are some virtual reality files to look at. Got the right equipment, but if you just got your iPad or an iPhone or your Android phone, you can download from those links and you can have a look around the vehicle structures and switch parts on and off. And the CAD and the CAE files are available from us. If the university want them, you can have them. Just need to contact me. I'll arrange for it. Any questions?
Thank you. Thank you, Peter, for such a nice talk. And I think, Evan, please ask your question.
Hi, Peter. Thanks for that. That was a really interesting presentation.
Thank you.
First question would be, did you consider pedestrian impact when you were doing the front crash scenarios? Because I imagine by removing the hood, you changed that situation significantly.
We didn't. Do realise that because it's kind of a flat-fronted vehicle, there's no bonnet there.
Mm-hmm.
But also that the vehicle has got radar, LiDAR cameras on, so it should automatically stop.
Absolutely, yeah. So,
which doesn't mean to say that if a child run in front of the car, autonomous car has got a decision to make. Does it move to the left and maybe mount the curb? Does it hit the pedestrian, or does it swing to the right and go into the oncoming traffic?
Mm-hmm.
People who write the software for electric cars and autonomous cars in the future have got a few decisions to make.
Absolutely. Tim, thank you very much.
Okay.
Thank you. Yeah, Didier, Yeah.
Yeah,
Good to
hello there. Hi, nice presentation. Thanks, Pete. Yeah, I just wanted to ask you in terms of crash worthiness and standard and indeed simulations, whether with EV and the more EV batteries being packed, there is a need to review all of that in terms of combining both the the mechanical, the high strain rate, but also with the thermal energy, just in case you have thermal runaway or explosions and so on. I don't know your views on that, whether it is treated similarly to a combustion engine, where you got that at the front or at the rear, or maybe in central positions of a car. But just wondering your thoughts on that.
This vehicle was designed for around 2035 launch, which means that you'll have both driven and autonomous vehicles on the road. So your autonomous vehicle has got to meet all the crash legislation that a current vehicle on the road has to meet. If in the future we have only autonomous vehicles, you can see that they would crash into one another. So you can see that the car manufacturers can then start reducing the amount of crash structure that vehicles have on them. Your second part of the question, I've forgotten. Sorry.
Well, it's just combining both the sort of a conventional crash analysis with the impact on battery and thermal runaway, maybe explosions and so on. I mean, I don't know if it's treated differently to a combustion engine with fuel, conventional fuel.
So at the moment, with the battery technology as it is, cars are getting heavier, which means the crash structures are getting heavier.
Yeah.
Battery electric car is 500 kilograms heavier than a petrol car or a diesel car today. Which means that the body-in-white has got to be stronger to withstand the crash energy. In terms of thermal runaway, I was asked this question last week actually by the JLR engineers, because they've been looking at it and they would want to use steel in their battery boxes because it's got better thermal conductivity than the aluminium.
Right.
So they're interested in that as a solution, a steel solution of steel in their battery boxes, because they may also be lighter than as well than the current aluminium ones that they're making. And it's all down to manufacturability. Current aluminium boxes tend to be extrusions that are welded together, so very cost heavy. Whereas if you can use one sheet of steel to make the battery tub, if you like, you get a big cost advantage. And Honda are doing that, if my memory serves me right. They're using a very formal DX57 to make the battery tub. So there's no joins in it. So it's then, obviously very cost effective, but it's also gets rid of a water ingress problem.
Maybe another one. So, quite interesting with your 64 steel concept, which I don't know how you can manage then the sort of the inventory around the car, but maybe it's needed. I don't know how much differentiations there is in modulus and yield to tensile ratios, elongations, and so on. But it goes opposite to the kind of a uni-steel type concept. And I was just wondering your views on that. Do we really need 64 or whatever the number is?
We didn't use 64.
Sure.
But 64 were available to Ricardo, the design consultants. And if you look at the list of grades, some of them were very close to one another. There was 20 megapascals difference in the yield and 20 megapascals difference in the tensile, but they were available in different parts of the world. If you constrict that table to maybe European grades, so you're not paying them some horrendous transport cost to get your grade from the other side of the world to here, that 64 would probably half. Again, that's only 30, so 32 grades. but you will find that various OEMs favour one grade over another, and that's the way they've always done it. So they will just use that their materials that they want to. They won't use the most economical to them or the most performance driven to them. They'll just balance it out.
Okay.
Because, as you know, as a steel company, we make X number of grades for automotive.
Yeah, and surveillance to customers and so on. Yes.
And not everybody makes the same grades. You know, we all make the common ones, but the uncommon ones, various steel companies, it's their speciality. But we have to include them in the toolkit that we give to Ricardo.
Yeah. Okay. Thank you.
Thank you, Didier. Any further questions? Yeah, please.
Hi, yeah, and not quite an engineering question, but you mentioned trying to aim to increase the occupancy up to around 3.
Yep.
Which to me sounds like it could be quite a challenge. So I wondered if there was any ideas in that aspect.
Yeah, difficult question. Us in Europe, we tend to all own our own cars and only take family and friends around with them. In places like India, they're more used to ride sharing taxis and auto rickshaws. Maybe it's a change of mindset that we'll have to adopt in Europe, and that if you're going to use this car just to go from home to Sainsbury's, there may be somebody else already in the car when you get in. It's not something we're used to. Change.
How important is that number in the the aim of getting to a lower carbon future?
It will become important because if you have 2 people in one car, the CO2 is X. If you have 2 cars driving to the same place or virtually the same place, it's twice X, isn't it?
Yeah.
If the country were trying to reduce our CO2 output, should ride share. It's not forgetting this is a concept for the future, just to demonstrate steel is a material that could be used for these type of vehicles.
Yes, Ivan. Again, please.
Yeah, another question. So, what would you say were the key kind of opportunities relating to the architecture that were enabled by an autonomous vehicle? So you mentioned, for example, you didn't need a body side as
no, we didn't
you
need
kind
a body
of incorporated
side.
that into the door. Were there any kind of other kind of key areas that you think could have scope for future use?
Well, if you look at the vehicle, it is virtually like a box on wheels. And there are a couple of OEMs also looking at similar type structures because you can put the motors are quite small. You can put them under the wheels, by the wheels, battery pack on the floor, so you've got like a running platform. The bonnet, as we know, is to cover the engine, so we have a long bonnet because the engine's quite long. Even a transverse engine car has got a short bonnet. If you don't need that space, and you then have a very, very short end, it does lead you down another path where you have to manage the crash energy, because we're in this mixed driving mode at the moment of autonomous and driven cars. Excuse me. Whether it will still be the same, maybe, who knows? Maybe when we start using these vehicles, we don't like sitting backwards by going forwards, like some people don't like sitting on a train, sitting facing backwards when the train's going. Other people don't mind. But if you can sit facing inwards, you get quite a large space in the middle. Whereas if you have to get in and then shuffle around the seat, face forward, it may mean that the vehicle has to get larger. On this study, the vehicle to begin with was about 100 millimeters shorter, but we had to lengthen the front end and move the front occupant rearwards by 50 mil and lower the front end by another 50 mil to actually get the crash performance, the impact performance that we required to pass the legislation.
So do you imagine then that if legislation were to reflect the reduced chances of an incident associated with using fully autonomous vehicles, then that's where the greater opportunities would come?
Yes, you'll be able to reduce your front end crash performance. So in terms of length, we can maybe knock another 150 mil off the front end, and you'll be virtually sitting on top of the axle. But if you're not going to crash, that doesn't matter, and you're not driving. So if it's not going to crash, does it really matter? It then becomes aesthetics or style, and you can see one train of thought going forward is that in the future, these vehicles will just become mobile hoardings where you can have advertisements on the side of the vehicle. So just flat-sided vehicles, but not today.
Okay, thank you.
Okay, thank you. Any further questions to Peter? Okay. If no more questions, I think thank you, Peter, once again for such a nice talk, followed by nice discussions with lots of questions. And again, on behalf of our group, thank you, and thank you all for joining the talk. Have a nice afternoon. Thank you very much.
Thank you. Yeah, thanks, Prakash.